What is up, everybody? In today's tutorial, you are going to code an actor-critic agent in the Keras Framework. As a bonus, you're going to see how you can implement custom loss functions to use loss functions that aren't included in the default Keras installation. Let's get started. As usual, we start with our imports. The Keras backend will give us access to functions like k.sum, which sums up a tensor, and k.log for taking the log likelihoods of our actions will be very important in our custom loss function. And of course, we're going to need several layers to construct our model, the activation, dense, and inputs. And we'll also need the model from Keras.models. We aren't going to worry about saving models for this particular tutorial. I have others where I show you how to do that, but for the lunar lander, it's not particularly important, so I'm going to skip it for now. And of course, we want the atom optimizer, and we want NumPy to handle NumPy type stuff. So we're going to stick everything into a single class, the agent class, and there's no magical inheritance in Keras like there is in PyTorch, so you just derive from the base object. And of course, your initializer is going to take not just one learning rate, but two, and the reason is that both the actor and the critic get separate learning rates. This isn't like deep Q learning where we're going to copy one weights from one network to another. We're actually going to perform an update on both models, and they each get their own learning rate, and they are different. We also need a gamma, which is our discount factor that tells the agent how much to discount future rewards. We need a number of actions in the lunar lander environment. Of course, that is going to be 4. Layer 1 size, we're going to default to 1024. I've done a lot of hyperparameter tuning on this. There is a significant sensitivity to the layer sizes, so I would encourage you to perform more of the hyperparameter tuning because I probably haven't found the best possible combination. But I'm going to settle on 124 by 512. And of course, we need input dims, and for the lunar lander environment, that defaults to 8. And of course, you want to save your respective member variables. And we're just going to perform a little sleight of hand here and rename it to FC1 dims and FC2 dims, just for brevity. Next, we're going to need to construct our actual deep neural networks. So what's really cool about this is we don't have to worry about convolutional layers since we're just dealing with an environment that has a single vector as an observation. But we are going to need an actor, a critic, and a policy. And that will be build policy network, a simple function we're going to define here in a moment. And we're also going to need an action space. And that's just a list, range self.n actions. Let's go ahead and save n actions while we're at it. I see I forgot that. So next up, we get to handle building our actual deep neural network. This is pretty straightforward. We handle that with the build policy network. You know, actually, I'm going to rename that to, because it's not just the policy, it's also the actor critic. So let's call this actor critic network. And we will rename it here, of course, actor critic network. And that just takes self as input because this is a member function. So first up, we need an input layer, and we have to define a shape. That will be self.inputDims with a comma indicating it's going to have batch size. No activation or anything like that, very straightforward. We need what's called a delta, and this will be related to the calculation of the loss function. So we have to have an input for that as well. And that is just going to be a one-dimensional input, nothing pretty complicated there. We're going to have a first dense layer and self.fc1 dims and an activation as ReLU, and it will act on input. You know what? I see I'm not actually using the activation, so let's go ahead and delete that. I copy a lot of stuff between files and do things different ways, different times, so stuff gets, replicated that doesn't necessarily need to be. So next we have the second dense layer, and that will output self.fc2dims. What's really cool is that the inputs are inferred here, so you don't have to worry about defining a particular input shape. That's just inferred from the model architecture, and that'll act on the output of dense 1. Next, we need the probabilities. So if you're not familiar with actor-critic reinforcement learning, what it does is you have two deep neural networks. One is an actor that approximates the policy. The policy is just a probability distribution that assigns a probability to selecting a given an action given some state. And a critic, which like critics in real life says, hey, that action sucked, you need to do other stuff. The critic calculates the value of that action. It's kind of like deep Q learning, where you have a table, or rather a representation with the deep neural network. We pass in a state and get a value of each action on the output. So the critic kind of approximates the V, the value function, for the particular action that was taken by the actor. And that's what the actor uses to guide its decision-making process by way of the loss function. So the probabilities, is just self.n actions, and the activation is not a ReLU, but it is a softmax. And the reason is that it is a probability function, and so the probabilities must sum up to 1, because that's how probabilities work, at least in this universe. Next, we have values, and this is what the critic network will output. That's also a dense, and that has one output because we're just dealing with the evaluation of a single action, and a linear activation, and that also acts on dense 2. So one other thing you can take note of here is that the actor and critic networks actually share these two dense layers. They are essentially a single network with two different outputs, and I found this very helpful in more complex environments like the lunar lander, whereas in something like the mountain car environment, you can get away with having two totally distinct networks with separate inputs and separate lower deep layers for the actor and critic respectively. In this case, we're going to have them share, and it works out quite well. Next, we come to the bonus material. So let's define our custom loss function. So in Keras, all custom loss functions must take the following arguments: y true and y predicted. And y true is defined as the labels we pass in. In this case, it's just going to be the action the agent actually took, and y predicted will be the output of the deep neural network. So just whenever you have to write your own custom loss function, keep that little tidbit in the back of your mind. Since we need to take a log of a number that could possibly be 0, which is bad, we need to do a little bit of clipping. So we want to say we want to clip y predicted, and we want to bound it by some small number, 1 e to the minus 8 and 1 minus 1 e to the minus 8. So we're giving it a nice bound to make sure we're not taking the log of either 0 or 1. And next we need to calculate a log likelihood, and that is y true. In other words, this will be a one hot representation of the action the agent actually took. So it's an array of zeros with a 1 in the index corresponding to the action the agent took. And you're going to multiply it by the log of the output, which is just the clipped y prediction. So that's why we need to clip it, so that way we don't take the log of 0, which blows up to infinity. So next we have to return k.sum minus log likelihood multiplied by delta, where delta is the input up here, and delta will be calculated in our learning function, and it's just the output of it's related to the output of the critic network. So if you I don't know if you can hear that in the background. My son is going crazy. He's playing with his mother. So if you're familiar with computer science or even JavaScript, this is quite prevalent there as well. This is a function closure where we're returning one function inside of another. That is how all custom loss functions are handled in Keras, and it's really a cool feature that you can implement your own loss functions that aren't included within the rather Spartan based library of loss functions. So the actor is just going to be a model with input defined by the input and delta, and the output is going to be probs. So this is effectively the policy, and you want to compile that with an optimizer of Atom with a learning rate of self.alpha. and the loss is just going to be the custom loss. Now you don't want to have the parentheses here because then it'll expect arguments. You just treat it like an object, so custom underscore loss. Next, we want to say our critic is also a model, and the input to that is just our input, which would be, of course, the observation from the environment, and the output will be the values. And of course, you want to compile that as well, and the optimizer will be Atom again with the learning rate of self.beta. And the loss will just be a mean squared error. So this will end up looking pretty similar to deep Q learning for the Critic network. It's not quite exact, but it'll be pretty similar. You'll see momentarily. So we've compiled that. Next up, we want the policy. And the reason we need two different things is because we want to train the network using this because we need the deltas. But when we're selecting an action, we don't take into account the input of the Critic. We just calculate the feed forward of the network, and so you need a separate thing to keep track or to do a prediction for the policy. Kind of a kludgy way of doing it, but hey, whatever works, right? So it just takes the input as input and outputs the probabilities. Very straightforward, and we don't have to compile that because we're not going to be doing any back propagation on that, so we don't have to worry about that. So we want to return an actor, the critic, and the policy. And that takes care of our deep neural network, so that'll just return here. And next up, we have a couple other functions. So if you've seen, many of my other videos, you'll know next up we have to choose an action, and this just takes an observation as input. So up here we define the input as having shape input dims, comma, so we have to do some magic here. We have to say state equals observation np.new axis. This will just add an axis of along one dimension. Then we need to say probabilities equals abilities equals self.policy.predict state, and it returns a tuple, so you have to take the 0th element. Next, we want to select an action, and that is through random.choice. We're going to select from the action space with probabilities defined by the output of our model. And of course, you want to return that action. Excuse me. Next, we have to handle the learning function, and this is a type of actor-critic models use a type of temporal difference learning. We're not using an actual memory here. You may notice I don't have a memory variable for the agent, so we're going to learn from a single state, action, reward, new state, and done flag. So it's just going to learn from a single example. That makes actor-critic an incredibly sample inefficient way of learning. It takes quite a few iterations to learn, as you saw from the learning plot at the beginning of the video, but it does manage to land the lunar lander on the surface and achieve a score of 200, which qualifies as solving. Or I think it's close to 200. I don't know if it gets there exactly, but with more training and more games, it'll get there for sure. So state, we have to do the same thing, not new axis, and same thing for state underscore np.new axis. Next, we need to feed these states forward through the critic networks. So we'll say critic value underscore equals self.critic.predict state underscore critic value equals self.critic.predict state. And just like in Q learning, we want to calculate a target, and that is just reward plus self.gamma times critic value underscore 1 minus multiplied by 1 minus int of done. And the reason we have 1 minus done is because when done is true, you don't want to take into account the value of the next state because the episode is over. And so it has to be 1 minus true or 1 minus int of done. Next, we have our delta, and that's just going to be the target minus the critic value. And we'll use that to train our actor network in a moment. So next up, we need what we have here is for the action an integer representation. We have to go to a one-hot representation because we're doing a multiplication here. So let's handle that. Let's say actions equals np.zeros 1 and self.n actions. Actions np.arange 1 sub action equals 1. And then you want to say self.actor.fit, and we have to pass in a state, the delta, and the actions. The actions are the y true, and the state and delta will go, the state will go into calculating the y predicted, and the delta will be used up here in the functional closure for the custom loss function. You also have to train the critic, so self.critic.fit state and target. I also forgot the verbose equals 0. That's so we don't get output indicating the accuracy and the loss. We don't really care about that for the training of our model, but this will handle all the training of the actor and critic networks. So they will both change in tandem, where the actor is responsible for choosing actions and the critic is responsible for informing the actor of the value of those actions. Very, very straightforward. This is really it. Only 60 some lines of code. Very, very simple and straightforward. Let's go ahead and code up a main loop to test it out. So let's say, of course we want to import Jim from actor, critic, Keras, import agent, from utils import plot learning, from we don't need to import the wrappers. That's for just generating video. You don't really need that. We need to import numpy as np, and that is it for the imports. So let's go to the main function. Name equals main, agent equals agent, an alpha of a very small learning rate, 0.12345, so 1 by 10 to the minus 5, and a beta of 0.12345, so a beta of 5 times alpha. And I think all of the, let me take a look over here, I think all of the defaults are good. 10, 24, 5, 12, yep, those are all good. So let's leave that. Now let's say env equals Jim.make lunar lander -v2, and score history equals an empty list, and num episodes equals 2000. We have to let this train for quite a while. With deep Q learning, of course, it solves the environment within about 150 games. It figures out how to beat it. This is much less sample efficient, and so it takes a much longer time to learn, but it is a simpler thing to learn the policy than the value function in the general case. Maybe not in the case of the lunar lander, but in general, actor critic turns out to be quite powerful and forms the basis for things like PPO and DDPG. So for I in range, num episodes done equals false, score equals 0, observation equals env.reset. While not done, action equals agent choose action, observation, new observation, reward done, and info equals env step action, agent dot learn, observation, action, reward, new observation, and done. And of course you want to reset the new state to be the old state, so that way you can select on based upon the current state and increase your score at the end of the episode. Sorry, at the end of the step. And at the end of the episode, you want to append the score, so that way you can keep track of your total score over time. And of course, you want to know how well you're doing, so let's calculate an average MP mean, and that is score history of the last 100 games. Whoops, there we go. And then print episode I score to F and average score %.2F score average score. Let's put that on the next line. And that is all that I want to print. And at the end, file name equals, I don't know, lunar lander actor critic.py. No, PNG. We don't want to save it as a PY file. Plot learning, file name, sorry. good grief, plot learning, score history, file name equals file name, and window equals 100, because that is a definition of solved for this environment. So that is it for the main program. Let's go to the terminal and see if I made any typos. So here you can see an output of another model I tried to run. This is what the terminal output looks like, and you can see it solves the environment, but the running averages are all over the place because this is a highly sensitive learning method. But let's go ahead and run what we have now. Let's say Python main Keras actor critic lunar lander, and it gets all of this crap because my install is borked, and I didn't make any typos. I think that is a first on this channel, the first time I have managed to get all the way through. That's incredible. I have to pop open a bottle for that one. But you can see it's learning, and here is the output of one such model. And at the beginning you saw the how the agent looks after it solves the game, manages to figure out how to land the module on the moon. Very good stuff. So this is actor critic methods. This is a type of temporal difference policy gradient learning. A little bit sample inefficient, a little bit sensitive to perturbations in the parameters, so it does tend to oscillate all over the place. It's a little bit less stable than deep Q learning in some cases. However, in many environments, it is much simpler to learn the policy than it is to learn the value function. So I hope this was helpful. If it was, make sure to share, subscribe, and hit that bell icon. I know only like 14% of you now have actually hit that bell icon and are getting my notifications. Leave a like, a comment, and I'll see you in the next video.